In your 1988 Gifford lectures entitled Infinite in All Directions, you offered a series of reflections grounded on your own involvement in a wide range of scientific fields. In particular, you put forward the hope there that the world might be found to be inexhaustibly rich. In recent years, there have been many strides made towards a so-called theory of everything. What are your views on these developments, and have they helped to confirm or question your original thesis?
Oh, the theory of everything, of course, is exactly the opposite of what I was talking about. And that implies that there's just a few things we have to understand, and that's it, and we understand everything. That's nonsense. The whole point of a rich universe is you don't understand it. And in fact, I mean, that's what's exciting about science. There's so much we don't understand, and every time you understand one thing, you find two more mysteries behind. And so that's what I'm hoping, that it goes on forever like that. So we certainly never have a theory of everything. That would be, to me, a disaster.
So you discussed there the rise of superstring theory as one kind of example of abstraction. Do you still maintain an interest in that kind of theory and in the drive to unify the theories of the fundamental forces?
No, on the contrary, I'm a diversifier.
You're a diversifier.
Not a unifier, yes. I like to explore the universe and find out how complicated it is. And this idea that everything should be simple is diametrically opposite. I mean, of course, both of them are true. And there are great strides in unification, but that's not what I do. I'm pushing the other way. And
pushing towards the infinite and the inexhaustible.
And the details. I mean, I love the details more than the big picture.
So butterflies rather than superstrings.
Oh, I wrote about butterflies and superstrings, yes, but that was sort of just a slogan. It's not what I do.
And so a major theme of your Gifford lectures, as well as your later research, has concerned the search for the origins of biological life. And in your lectures there, you proposed a hypothesis of dual origins, in which life could have evolved first in protein form and later in nucleic form, and then that these two aspects combined through a parasitic or symbiotic relationship. Do you think biology is any nearer to answering questions of life's origin now?
Well, of course, it's got a lot nearer in the sense that we've understood a lot more details, and of course, in a way, that makes the problem even more difficult, since the more details you know, the more difficult it is to understand what really happened. And so I would say that theory of mine is still alive, but there hasn't been any evidence either for it or against it that's conclusive. I would say everything we know is consistent with that, but that doesn't mean it's true. And I would say I would rather incline to think that there were many stages before proteins and before nucleic acids. I mean, that was probably the end of a long process of building, and we don't know what the earlier stages might have been.
So do you have any further ideas, or have you nuanced that thesis at all?
Well, I talked to biologists who are actually doing the work, and well, there are some interesting things have happened, but there is no plausible chemical route from the original inorganic world to life. That's still a huge gap which has not been filled. So there are no experiments, as far as I know, which really explore that. And
would you be able to say a little bit more about the main options that are out there in terms of the origins of life and how your theory relates to them?
I wouldn't call it my theory. This is a view that's held by many people long before me, and it's just a question of what order you think things developed. I would say the first stage must be garbage. And probably the first approach to life was just little oil droplets of some sort which floated in water and collected chemicals. And that was essentially garbage collection. That is, big molecules would tend to stick inside these oil droplets, and small molecules would tend to leave, just for thermodynamic reasons. So they would act as collectors for big molecules, And then you get interesting chemistry going on, but God knows what it was. Or certainly I don't have any detailed theory of that. And then suddenly, a couple of billion years later, there come these real cells which know how to metabolize and reproduce. And how you get from one to the other is the big question.
So it's really still a very patchy story.
Completely patchy.
Completely patchy, even in the years since you wrote.
No, there hasn't been a lot of progress, I would say.
Okay. And how has the dual origins theory been received by other scientists?
Well, it's not generally popular. I think there's a tendency among biologists to believe an RNA world. An RNA is supposed to be the magic stuff which came first. I don't believe that, but I mean, they may be right.
Why they believe that RNA came first, and
Well, that was the sort of prevailing dogma, which originally was propounded by Manfred Eigen, I believe. Anyway, and of course, there's a lot of evidence, which is very strong, that RNA was extremely important, and the fact that ribosomes, which are the sort of the chemical factories in our cells, are made of RNA. That's a very important fact. And so if those were RNA, then presumably what came before was also RNA. And so the RNA clearly was an important player. I don't think it's likely that that was the first thing.
So RNA comes a lot later in your theory. It's the proteins that come first, and then...
Well, I wouldn't say proteins come first at all, no.
Oh, okay.
No, proteins also, of course, are very complicated.
Yes.
And probably lots of things came first before that.
Okay, so as a diversifier, you began your career in theoretical physics and quantum field theory. And
well, not really. I began my career as a mathematician.
as a mathematician.
And I'm really an applied mathematician. That's what I do. My skill is just mathematics. And so I find problems where mathematics can be applied. And some of that happens to be physics, and some is other things.
Yes, and so so this idea of diversifying and the richness of the universe is what prompted you to move it to apply widely and move in from physics to maths and space
I don't
science.
know whether that's true. I mean, I'm just always improvising. I don't have a plan of how I'm going to spend my life. I'm more or less just an opportunist.
And so with mathematics, I believe in your book, one of the reasons you propounded for the universe being inexhaustibly rich was to do with Gödel's incompleteness theorem and the idea that not everything is provable, that there are some non-provable statements. Would you be able to elaborate more on how that links into the theory of everything?
So that's certainly true. I mean, Gödel proved that mathematics is not a closed system, that there are always questions that cannot be answered within any given set of rules. And that's a wonderful and profound understanding. So it means mathematics certainly is a constantly growing subject and will always be so. And so it's likely the rest of science is the same. And of course we have now Turing. Turing did the same thing for computing that Gödel did for pure mathematics. And Turing proved that there are universal computers that can compute anything that any computer can do, and that even they cannot answer all the questions. So there is a similar situation there. And of course nowadays most of science is done with computers, and so we know that is also an inexhaustible territory.
Yes, which offers a much more kind of vibrant picture of the universe and wrapping everything up in the theory of everything.
Exactly.
And have you even though you're a diversifier, have you still retained an interest in developments in quantum field theory and quantum gravity and all of those kind of...
I would say a certain amount of interest, but I don't really keep up with it. And I talk much more to astronomers. And astronomers talk a language I can understand, and
Yes.
as a physicist tend now to talk a different language.
And as an applied mathematician, how would you explain the remarkable fit between mathematics and the universe?
Well, that's a big mystery too. I don't pretend to explain it. It's a fact, and it's something very wonderful that we're grateful for. But why it's true, of course, nobody can tell.
So it's something always inexplicable then?
Well, maybe. I mean,
Maybe, or you're just, yeah.
It certainly looks that way.
Okay, and I believe you're well known for taking interest in the science and technology of the future as well.
Yes.
And in forecasting scientific innovations of the 21st century, you named 3 areas of particular importance: advances in molecular biology and genetic engineering, development of intelligent machines, and the beginning of the colonization of space. Would you still be confident in making such predictions now?
No, I'm never confident about making predictions, of course, but I mean, predictions are not supposed to be right. They're only to stimulate the imagination. And
Yes.
they don't, usually predictions are wrong, and including mine. And so we'll see what actually happens. I mean, I would certainly add to that list now neurology, which seems to be the science which at the moment is making most rapid strides. And it's also a very profound question how human brains actually work. And I think we're coming closer to being able to grapple with that. So I would say for this century, I would certainly put neurology on the list. And of course that goes with computing, since there's this general belief that there's something in common between brains and computers. But I have again, a heretical view about that. I think the future is analog and not digital. And Turing, of course, invented the digital computing and was such an enormous success. Everybody imagines now analog computer means a slide rule. It's something our grandfathers used, but it's totally obsolete and old-fashioned. And analog computing machines are thought of as just sort of prehistoric, not of any current interest. But there is a theorem. Actually, a theorem was proved rather similar to Turing's theorem. I mean, Turing in 1936 wrote a famous paper on computable numbers in which he proved that digital computers have this power of imitating each other, and so one universal digital computer could do everything, whereas a similar theorem was actually proved for analog computing about 30 years ago by 2 mathematicians called Pourel and Richards, which is completely unknown. And it was published, I think, in 1980, and I found it very exciting. It's a sort of analog of Turing, but for
analog systems,
analog machines.
Yes.
And so they give the paper. What the paper proves is that there are numbers that you can compute analog, which you cannot compute digital. And anyway, that's a fact, and which has been disregarded now for 30 years.
Right.
But I think in the long run, analog will come back, because I believe our brains are probably analog more than digital. When you look, and we don't understand much about what goes on in our heads, but what the brain is conspicuously good at is picking out memories very fast. So you see a face, you know immediately that that's your friend Guy, and in a fraction of a second, you identify the image with something in your memory, and we do the same thing with spoken language, that you understand speech instantaneously in a fraction of a second.
Yeah.
And it looks more like an analog process than a digital process. The ability to compare images very fast and sequences of sounds at lightning speed. And that looks to me as if it's probably an analog process. And anyway, we'll see. But I think one of the reasons why artificial intelligence hasn't happened is because we've been using digital machines to try to simulate an analog brain,
Yes.
and it doesn't work.
So do you think that the brain is effectively reducible to a complex analog computer, a highly complex analog computer?
Well, I would say it's more likely than that it's purely a digital computer. I mean, obviously it's a mixture of both, but I would say probably it'll turn out to be mainly analog. But that's a complete guess. I could very easily turn out to be wrong. But anyway, it looks like if that's true, then artificial intelligence will only begin when we start to think analog rather than digital.
Yes. So we need a revolution in our thinking in that direction.
Especially a revolution in computing.
Yes. And do you think then that's not any nearer to happening at the moment?
No, on the contrary, everybody still is in love with digital, but there are signs. I think Facebook is a sort of example of computing becoming more analog. That, of course, wasn't planned that way, but it's happening. That the world of information is turning more to pictures and less to symbols.
And is there any connection with quantum computing, or is that entirely a separate matter?
Quantum computing is totally separate.
Totally separate matter.
It could very well turn out to have an important role. The brain may be a quantum computer for all we know.
Yes, yes.
So, I mean, certainly quantum computing is a third player, which we understand even less.
Yes. And so with your other interests, astronomy and space science, what have been the developments there? And is there any sign of us moving back into space or towards the colonization of space?
Well, there, of course, again, there are two totally different worlds. There's the world of space science, where humans are completely superfluous, where we send instruments, and that has been spectacularly successful. And I mean, the most recent mission which I've been concerned with is that the Kepler, which is searching for extrasolar planets,
Mm-hmm.
which is a spectacular success. And of course it's an unmanned mission, it's not very expensive. And they found hundreds and hundreds of these planets. So it's transformed our view of planets completely. And so that's a huge success for space science.
Yes.
But on the contrary, the human space program, of course, is a disaster.
Completely faltered.
It's completely stuck in the mud, and nothing has happened in the way of human adventure in space since the days of Apollo 50 years ago, and that doesn't look promising at all. I think it will happen, but only when it becomes cheap, and the question when it becomes cheap, of course, is completely up in the air. We just have no idea. So I would say betting on this century is probably a mistake, but it remains to be seen. But anyway, it could happen in this century. Now I think if I made the statement again, I would say next century for that. And the colonization of space really, it's not the right word. I mean, it's the expansion of life into the universe, which is really at stake, and it's not just people. And if we can bring life into the universe and establish new ecologies all over the universe, then it will really make sense. But human colonies are only a small part of that.
Yeah, so the connection with Kepler is evident there, for finding extrasolar planets which might be capable of life.
That's, of course, the first step, yes.
Yes, and getting there is the second step.
Yes, and there may be things in between. There are probably lots of objects in between us and the stars, which we don't know about. And there's probably a huge population of planets which are not attached to stars, so which may be much easier to reach.
Thank you very much, Professor Dyson, for offering us a view of the universe as infinite in all directions.
Thank you.